we are Team 19, and today we'll be going over the design of a mechanical keyboard. My name is Lorenzo Spagnolo, and I'll be presenting alongside with Michael Getty, Brian Drescher, Alex Avila, and Nicholas Weller. As mentioned, we'll be going over the design of a mechanical keyboard, which is used to input text and commands into a computer. Our keyboard will be hardwired into the computer using a USB and will feature the standard QWERTY design found in most keyboards. The key components consist of the key assembly, as seen on the right, that fits into the overall assembly with the exterior shell, base, and mounting plate. This goes along with the PCB, which is simplified as a basic electronic component for our design. Our production volume will be 100,000 units per year, and this will be going with our primary and secondary customers. Our primary customers are businesses, which are looking for a reliable, basic design that is cost effective, and our secondary customers are home users that also benefit from the reliable design, but they will not be able to customize this keyboard. Next, we have our functional analysis or FAST diagram, which stems off of the basic function of processing text. This then stems to generating signals, processing signals, and providing feedback, which is followed along with the four standard features of enhancing the product, ensuring convenience, assuring dependability, and pleasing senses. From our FAST diagram, we now have the function component mapping matrix, which maps all the components shown in slide 2 to all the functions of the keyboard located on the top. This then helps us designate what components provide what functions in the keyboard. Next, have the quad chart, which shows the importance of all the components and how that relates to their manufacturing or assembly costs. As seen, all the components have high functional importance. However, for manufacturing or assembly costs, the PCB, faceplate, and mounting plate will have the highest costs. We'll look at product family design, which shows the differences between the primary and secondary customer variants. First, we'll look at the functional differentiation table, which designates the different functions between the two variants. As we can see, selecting data will be the function that establishes the difference between the two variants. Next, the component commonality table links the functions to the components in the keyboard. As we can see, the keycaps accomplish the function of selecting data, which can be seen in the function component mapping matrix on the previous slides. This leads the keycaps to be our module. In terms of differentiation between the two designs, as seen here, the secondary customer design will feature a divoted or indented keycap on top that allows for a more ergonomic design. This will be tailored toward the secondary customer or home user. The top of the keycap will be different between the two customer groups. The bottom will feature the same cross design that will mount onto the stem. This will allow both variants to slot onto the stem in the same way for ease of assembly. Part of the product family design is the assembly sequences. Before delayed differentiation between the two designs for the primary and secondary customers, we can see that adding the keycaps before the PCB and computer connection created differences earlier on in the assembly process. By implementing delayed differentiation and inserting the keycaps last, the remaining components that are the same between the two product variants can be assembled all together, and then the keycaps can be added last.
Next, the team assessed the manual assembly design of the keyboard. After assessing all the individual parts, the team reached that the total time to assemble the keyboard was 5,223.8 seconds. Assuming a labor cost of $15 an hour for an assembly line worker, this determined that the total labor cost of the assembly was $21.77. This resulted in an efficiency of 0.17%. The low efficiency and high labor cost and total assembly time resulted in a few design changes for the manual assembled keyboard. The first key design change was that the fasteners, which used to be screws, were eliminated and replaced with snap fittings. To allow for easier assembly of the snap fittings, the team also added locating pins and slots to allow for workers to more easily assemble their pieces. Next, the team focused on redesigning the key module. The first key design change was eliminating the keycap from the key module. Additionally, the team decided to create an integrated stabilizer design, which eliminated another key part of the module. To replace the keycap, the team added a silicone cover for all keycaps. These three design changes eliminated two key parts from each of the key modules and only added one part for all 88 keys. After taking several design actions, including eliminating the stabilizers from the key modules, eliminating the keycaps from the key modules and replacing with a single silicone pad across all keys, and switching to snap fits rather than fasteners for the faceplate, the team's total time for manual assembly decreased to 3,877 seconds, thus resulting in a labor cost of $16.16 and an efficiency of 0.23%, an improvement over 0.17%.
For the automated assembly, we will also look at the key switches subassembly, as each one is made up of small parts that can be fed in an automated process. Also, there are 88 key switches for each keyboard, meaning that 8.8 million switches are needed a year for our volume. Automation would help with that. For the initial analysis, it cost $1.68.5 per switch, or $148.28 per board. To decrease the assembly cost, we did the following. First, the stabilizer and stem were combined into one part. The new stem is more expensive than each part separately, but it's cheaper than the stem and stabilizer combined. The second was making the bottom housing symmetrical so that it could be fed in more than one direction. The third change was adding a shelf onto the outer housing to help orientate it as it is being fed. It can only be fed one way, but before the differences were only minor. The shelf helps to better align the part. After the changes, the cost of the assembly went down to 86.1 cents per switch, or $75.76.8 per board, which is 51% of the original cost of the assembly.
For the process selection of the mounting plate, we determined that the key dimensions were the perimeter length and width and the locations of the keys. By looking at the functional component mapping matrix, we determined that the most important function was locating components. With this, we determined that the critical dimension were the key locations. We designated a tolerance of plus or minus 0.1 millimeters to ensure that the locations were accurately placed for further assembly. This slide shows the rest of the properties for the mounting plate. We chose 1100 aluminum alloy as the material for this part. Given this material, there were 9 processes compatible. Going through the capabilities of each process narrowed the choice down to sheet forming and machining. We recommend sheet forming as the final process recommendation because it can produce more consistent parts at a higher rate to reach that economic batch size of 10,000. Within sheet metal forming, we recommend the part off process instead of blanking. For the process selection of the rear shell, we determined that the key dimensions were for the orienting features and the snap fit locations. From the functional component mapping matrix, we see that the functions are to provide protection and locate components. Locating components needs to be more accurate to ensure a consistent and efficient assembly process. For this reason, we determined the critical dimensions to be those of the orienting features. We used a tolerance of plus or minus 0.1 millimeters to ensure the accurate placement of these features. This slide shows the rest of the properties for the rear shell. We chose ABS polymer as the material for this part. Given this material, there were 7 processes compatible. Going through the capabilities of each process eliminated everything except injection molding. We recommend injection molding as the final process recommendation for the rear shell.
Here we decided to apply the principles of DfM to a part manufactured using sheet metal, the mounting plate for our keys. It's made of 1100 aluminum alloy and had a cost of about $4.57 per part before DfM was carried out. We used DfM Pro as a starting point for how we would redesign the part. We redesigned 3 aspects of the part through our application of DfM. We smoothed out all of the sharp corners. We also eliminated narrow features such as the screw holes along the outside of the plate, as they were unnecessary to actually mount the plate to the overall assembly. Lastly, the part will be part off rather than blanked for more efficient shearing. Here's a screenshot of the redesigned part. Eliminating the screw holes very slightly reduced the cost of materials. The biggest cost reduction from our redesign came from the initial cost of the die, which decreased by roughly 9 cents. Over the course of a 100,000 unit production run, we estimate that we would save around $9,000. We uploaded 3D models of both the initial and the redesigned part to Hubs to obtain a rough cost estimate. Hubs only provides automated estimates for 500 units or less, so we found a power law fit for the provided data and used it to extrapolate the cost for a production run of 100,000 units. We also applied DfM principles to one of our injection molded parts, the rear shell. Manufactured from ABS, it had an initial cost per unit of $4.05. Again, we used DfM Pro to find ways to redesign our part. We redesigned 3 aspects of the part through our application of DfM. We changed the part to have a more uniform wall thickness, both reducing volume and material cost. We also added draft angles and rounded off all of the quarters of the part. We saw significant reductions in cost following the redesign of our part. As previously mentioned, making the wall thickness of the part more uniform resulted in a large amount of material being removed from the middle of the part, greatly lowering both material cost as well as operating cost. Simplification of our part also resulted in a minor reduction in overall bolt cost. In total, we estimate that the redesign would save roughly 99 cents per part, or nearly $990,000 over a 100,000 unit production run.
The final consideration for our design is the product service system. Our keyboard integrates with a mouse, computer monitor, and computer housing to allow for the full functionality of a computer. This integrates with the standard interface of the USB connection. Computer programming within the computer can allow updates and software changes to the PCB inside of the keyboard to increase functionality through shortcuts. This concludes our presentation, and we'll now take any questions. Thank you for your attention.